Representation of dynamical variables by operators. Position operator is represented as r cape psi, which is equal to r into psi. That means position vector r is simply multiplied with the wave function. Momentum operator, say in one direction, in x direction, p cap is h by 2 pi I del by del x, or minus I h cut d by dx. Energy operator E equals to I h cut del by del t. If we consider a particle moving in the x direction with velocity v, the equation of its motion can be written as a double in the form of double differential equation del square y by del x square equal to 1 upon v square del square y by del t square. Solution of this differential equation shall be y equals to a e raised to minus I omega t minus x by v. This equation, this solution comes from the classical mechanics. Therefore, if the psi is the solution of this equation, so the wave function becomes psi equals to a e raised to minus 2 pi I vt minus x by lambda as shown here. Now, using de Broglie and Planck law for lambda and e, we have two equations. Putting these two equations in equation number 1, we get psi equals to a e raised to minus I by h cut et minus px into x. We say this equation of psi is equation number 2. Now, if we partially differentiate this function psi with respect to time t, we get a solution where this term a into e raised to minus I by h cut et minus px into x, this term is psi. Therefore, from equation number 2 and 3, and this is equation number 2. So from equation 2 and 3, we get a solution that is del psi by del t equal to minus I e by upon h cut into psi. Or we can write e psi equals to minus h cut by I del psi by del t, or the operator e is I h cut del psi by del t. This is equation number 4, and this is the operator of energy. Therefore, by differentiating the function psi partially with respect to time, we got the energy operator. Similarly, if we differentiate this wave function with respect to x, we will get the momentum operator. So when we differentiate psi with respect to x, we get some solution, some simplification, and here we can say del phi upon del x equal to minus I, it is not minus I into px upon h cut into psi, or px psi equals to minus I h cut del psi by del x. Similarly, the operator for momentum in x direction, that is px, is minus I h cut del by del x. Similarly, py, pz can be written. Also, px square, that will be useful in forming the Schrodinger equation. Px square equals to minus h cut square del square by del x square. In short form, we write p square equals to minus h cut square del square and p equals to minus I h cut del. Now we are going to derive Schrodinger's equation. We write the total energy of a system as it's in the term of its kinetic energy and potential energy. The first term p square by 2m is kinetic energy and second term Vr is dependent on only position, that is potential energy. So p square is minus h cut square del square that we have put here. So h equals to minus h cut square by 2m del square plus Vr. Now we know h psi equals to E psi, that is Hamiltonian operator on psi gives eigenvalue E into psi. We can also write it as minus h cut square by 2m del square plus Vr into psi equals to E psi. So this is time independent Schrodinger equation. We can also write it as this. But we know from equation number 4 E is equal to I h cut del psi by del t. Using this in equation number 7, this is equation number 7, using here energy operator value. So we get a new equation minus h cut square by 2m del square plus Vr psi rt, which is function of r and t, equal to I h cut del by del t psi rt. So this equation is time dependent Schrodinger's equation, and this is time independent Schrodinger equation.